Buenos dias, everyone. Today we are going to continue our adventures into assembly land and learn more architecture. It's now week 5 of the class. Next week there will be a midterm, and it will cover everything that we have covered so far. So, one thing that I think is the most useful for you guys right now is the programs are starting to get complicated enough that you guys are kind of having trouble debugging them, right? Like, it's not working, you don't know why. And it's like it's seg faulting or something. So let me just type out some of the mistakes. So confusing branch versus branch with link. Like about 5 or 6 students made this mistake. Branch is used for if statements, for loops, while loops, basically anything within your code. Okay. Branch with link is used for function calls. Don't mix them up, because branch with link sets the link register, and so when you if you do multiple BLs within your own code, it's not you're gonna probably screw stuff up. So no cout option. So like I said, you guys could make your own function, right? You can make a print. You can make a print int function or something like that. Extern. Let's see, main.c. You could make just like a void print int function. That's allowed. Printf. Make that. You could have put it in your extern C code. Make a new file. I said slap it into your make file, and then it'll link together, and it will print a number. So okay, yeah. So the things that didn't work: BL versus B. Number 2, BL with set. I don't believe works. I experimented with it, trying to get my runtime down. I don't think it works. Debugging. So you can make your own print function, right? Or you can learn to use GDB, which I guess I can go over today. BLS would work as long as BL called has no compares. I don't know. Yeah, but that is another thing. So if you do like a branch with link equal to upper, and then you do and then branch with link not equal to lower, this code probably won't work, because the upper call will do a compare in it, probably somewhere, right? And so let's say the upper call does something and leaves the secret code program status register, CPSR, in such a state that not equal is valid. When you come back out of upper, it'll then do the lower and undo the effects of your code. And so you have to be careful. Don't use the suffixes when you're doing function calls, or after there's a function call. Don't expect the suffixes to be valid anymore. This one would work, right? This one would work, but you can't know if this one will not also take place. Okay. So I tried compiling debug symbols to run GDB, but it wouldn't compile. I think I had that issue. All right. So we can talk about GDB a little bit today. Okay, what else? Oh yeah, how to access memory. So base plus offset is a very common way of reading from memory. If you guys have read the textbooks, you'll notice there's like 8 different ways you can load from memory. More if you count. You can load a byte or a half word or a full word, and then you can just load from a number or a variable base plus offset with or without write back. There's a lot of different ways you can read from memory. There's also load multiple and store multiple as well. There's a lot of options, and you can go through the book. All you needed for this one, though, was just this. So, like, LDRB, load into register 6 from register 4 plus register 5. Right, so R4 is base, R5 is offset. Although, honestly, if you put them in the other order, it doesn't matter because it is addition. So in this case, like, if R4 is the string passed in and R5 is I, the loop counter, then you would add 1 to R5 every time, and you'd load 1 byte at a time out of the string, and if you ever got 0, then you would bail out. Okay. The issue of branches, yeah. If you try to get too clever, you can trip yourself up. So what I recommend when doing these things is to not be too clever at first, and, try and do this kind of stuff or this kind of stuff. I would start off slow and then refactor into something fast and save your old code as well, so that when it doesn't work, you can fall back on something that works. Okay. So let's learn about GDB. Okay. So CD into if got reference. All right. So GDB a.out. That's how you. I don't know if I have debugging symbols turned on. So inside of your make file, inside of your make file, you want to have -G enabled. That puts debugging information in everywhere debugging information is available. Oh, this is using the assembler. Interesting. I don't know what flags the assembler takes off the top of my head, so I'm just going to make this GCC, because GCC will figure it out. CD flags. That's a makefile variable, by the way. Like I think I told you guys, the syntax for makefile was made by a guy just on a whim, and he went on vacation. By the time he came back, this weird syntax had been adopted throughout his organization. It was too late to change it. So that should be good. So that's a variable. That's a makefile variable. Make clean. So anytime you change something like this, like I'm putting in the debugging information, typically you'll do a make clean to erase all the .o, the executable core files. And so this is, you'll see this in pretty much every makefile in existence or some variant thereof. And you notice that make clean is not dependent upon anything. And so if you just type make clean, then it will run this every time because it has no dependencies. Whereas if you tried rebuilding main.o, like if I said make main.o, it would rebuild just that one line. If I tried running it again, it would say main.o is up to date. But if you say make clean, it'll run every time because it has no dependencies. Okay. So if there's a dependency, makefile will not run again, because what make does is it looks at the timestamp of this file, looks at the timestamp of this file, and if this guy has been more recently edited, saved, let's say, than this guy, then it will run this command here and expect this to be updated as the result of it. Okay. So make, and then ASAN if no such file or directory, -C.
Shouldn't it be AS instead of GCC?
No, GCC can do that, but GCC will invoke AS for you. That's fine. I'll just put in the debug flag there. Yeah, you don't actually have to have any calls to LD or AS. If you see people doing assembly stuff, like rather than this, you'll see them do like LD-O, a.out, main.o, ASAN if.o. Like you'll see people actually call LD, you'll see people call AS, things like that. But in reality, the GNU compiler suite will figure out which step you're supposed to be doing, and will invoke the appropriate tool for you. It is slower, as we found out. It's very slightly slower, maybe. It wasn't a very scientific test. Okay, so if we run it, there's our code. Ask them if, and let's say it's not working right. Okay. The imposter syndrome is intense right now. It looked funky to me. Maybe it didn't come out right. In your VM is GNU stud GNU 99 necessary for GDB? No. So this is it's part of the C flags, right? So basically, every time we compile the code, it's usually a good idea to tell the compiler which version of C, in this case, we're using. C++ matters a little more because there's a really big difference between modern C++, C++11, and ANSI C++, which was 98. There's a huge update there. For C, there's some differences. One of the big things is you want to have // comments. That wasn't actually part of the C language until I think 99 was when they allowed it. And so usually when you compile your code, you need to have what standard you're using just in there as just a good idea. Because like, let's say you move this to another system, you try compiling it, different versions of GCC and G++ have different versions as the default. So C++11 was not the default until just a couple years ago. And then a few years after that, they made it 14 as the default, I believe. And so if you move to an older system, the compiler might support C++11. It's just not the default. So if you compile it without the std flag on there, then your code won't compile because you're using C++11 features, like range-based for loops and things like that. It just won't work. Okay, so yeah, okay. All right, so let's do this. So GDB a.out, reading symbols from a.out, done. And then we can break on main, and we can disassemble main. And so this will show you all of the assembly code for main. By the way, this is not, we're not in our assembly code yet. This is main. And hit return for more, and you can actually look at all the assembly code that's about to be run. This is actually in the executable. This is actually the assembly code in the executable. It's in the object file format, but it disassembles it back to assembly. And so you can use this. You can use this tool to hack copy protection and things like that. I noticed that std is set to GNU 99. And I usually see a version of C++ in there. Now, so GNU 99 is C, not C++. It's C. So when you're using GCC, you're going to use a C standard. And when you're using G++, you're going to use a C++ standard. And the C++ standards are going to be one of 98, 11, 14, 17, and 20, which I think currently is called 2A, although that should standardize into 20 at some point. And then if you're using C, you're going to use one of the C standards. In this case, we're using the 99 standard. And the GNU, rather than C99, we're using GNU 99. And the GNU people, the GCC people, have their own extensions to the C99 standard. And by using GNU 99, that enables those standards, those extensions to the standard. Like for a while, // comments were not actually part of the standard, but the GNU compiler allowed them anyway because everybody preferred them over /* and //. Okay, so did this code not make a function call? Branch with link. Printf. Branch with link to exit. Is this my inline code? Then main.cc, main.c. Are we doing the inline version? Yes, we are. Okay. Well, that's why. That's why I wasn't calling the function. Okay. Make clean. Make, I don't think we need to make clean there, but it's pretty fast to rebuild. On a big project, make cleans are the devil, right? Because you change one thing and then you need to rebuild everything. And this is really annoying when you're working with header files. When a header file changes and the header file is used by everybody, you have to do a full rebuild. And you change your make file to, you know, change a compiler flag or something, and everybody needs debugging turned on now. Make clean, make, and now you go get some coffee, right? Like when I was working in an office, people were like, "Why are you always in the break room drinking coffee?" I'm like, "My code's compiling," you know, and I'd just be sitting there reading a newspaper or something, you know, because it's super annoying, and then it doesn't work. And you have to change it back or something. There goes another, you know, half hour of your life. I mean, or worse, right? If you compile GCC or G++, if you compile that from source, you know, 8 hours, 10 hours of your life, you know. So if you do a full recompile, that's why I like package managers, because I mean, a lot of true Unix people build everything from scratch because they want to be able to have the source code and add any features they want and change the make files to their needs, and then spend 8 hours compiling. And I would rather not. Okay, so let's do this again. GDB A.out. So GDB is the name of the GNU debugger. It was written by my boy, and GDB. No manual entry for GDB. Unacceptable. Anyway, it was written by my man Richard Stallman. GDB A.out. Okay, so when you say GDB A.out, that launches the GNU debugger and it loads the executable. And then if you just want to run the program, you can just type run, and then it runs your program inside of the debugger. And this can actually be nice if your code's crashing, because then let's make it crash, and I'll show you that, I guess, first. Vim main.c. Remind me to take this out. So inside of this for loop here, if loops equals 5, A is equal to dereference memory address 0. See if that works. Might not like that. Make a pointer then. Int pointer equals null. Let's say you do null pointers in C, and let's dereference pointer. So that should dereference a null pointer, and we run it. Really? Didn't crash. All right. A is equal to 5 divided by 0. It's 5. Loops is like a million, right? Not helping me out crashing here, boy. Come on, you guys are students. Help me crash your code. Loops will never be 5?
Yeah. Loops.
Oh, damn it. Yeah. Yep. Thank you. Okay. All right. Yes. Thank you. A is equal to dereference pointer. There we go. Seg fault. Okay. And so if you guys are running your code and you just get a random seg fault, it can be very frustrating when you're doing assembly development. Clearly, I need more coffee right now. I know. I'm just not good at getting my code to crash. I'm sorry. It's like, you know, if you get shot a lot of times, you develop an immunity to bullets, right? Like that's just how it works. You know, your code crashes so many times, you just become invulnerable to seg faults. Okay, so this is not a helpful message, right? It's like when you guys are doing your coding, and it's like seg fault, you're like, where? what line, right? Because when we're doing C++ development, I've got address sanitizer turned on. And address sanitizer will detect that and report on line 42 of main.cc, you dereferenced a null pointer. I ain't got any of those supports now. So you might notice the difficulty level goes up just because your support isn't as good. You guys with me on this? Like, it's harder to do assembly programming, not because it's really hard, right? Like, everything's pretty simple. It's harder because your tool support is lessened, and you're working at a low level, and you make one mistake between a B and a BL or something like that, and, you know, seg faults, and it doesn't say why. So, you know, you guys with me on this? So, so GDB is your answer here. So GDB a.out, and we could just run it. And if we run inside of here, it will crash. And look, it tells you what line it crashed on. Cool. Neat. Okay. And so we are currently on main.c, line 51. You can hit backtrace. If you're within a function, backtrace, or I can spell it out for you. Backtrace will show you which function you're within. So function A calls function B, calls function C. You can hit backtrace, and it'll tell you what line of function A, what line of function B, what line of function C, what line in main you were in when the code died. And then you can do things like print the values of variables. Print I. I is 5, right? And so GDB has knowledge of all of the variables you have and their current values and things like that. If you want to print A, tells you the value of A and, you know, the value of the different variables you have set. Loops is set to 1 million. 10 million? 10 million. Okay. Is that a real story? Yeah, there was a guy who was paranoid about being assassinated. So he developed an immunity to poison, but then when he tried to commit suicide via poison, he couldn't kill himself. Can I print registers? Yeah, great question. So it is... info registers. Yeah. So you type info R, then it will show you the value of all the registers at a time. So so apropos, by the way, is the help system. So if you say apropos print, it'll show you all the different things that show you how to print things. So apropos register, it'll show you all the different commands related to registers. But the answer that you want is info registers, right? Info registers. Yeah. Or info. GDB has a lot of shortcuts. So IR, yeah. So there's a lot of shortcuts. I wonder if IR works. I don't think so. Yeah. So info registers, and then it shows you all the registers, and then you can step. Oh, your code's dead. Yeah. So let's get out of this. Vim main.c. Let's GDB a.out to find the line you are crashing on. Code runs fine now. Okay, so GDB a.out. And now if I were to just run it inside of GDB now, it just runs and then it quits, right? So if I tried doing like info registers, it doesn't work because it's already done. And so this is not, it's like, but I want to see what my code is doing. It's not working correctly, right? And so what you can do is you can put a breakpoint on, was it ASAN if? Was it break ASAN if? Okay, and then if you run it again, then so break means set a breakpoint. Okay, and so what that means is the debugger will run your code, and when ASAN if gets called, it stops and it drops you into the assembly zone. And so you can do things like say info registers, info registers, and it'll show you what the values of all the different registers are. And then you can do next, and it'll go to the next command, and then you could print the values again, and then go next, and then print the values again. You guys understand? And so breakpoint, next, step also does it, yeah. And so you can step over a function call, or you can step into a function call. So like if you have a branch with link, whether or not you go into that function call or you step over it. Yeah, and then when we step, it'll go back into main. So we're back in main, right? And it switches back into C mode, and you just sit here and step one at a time, and you can print print the value of index. Is optimized way fine. Print a, and then you can sit there and step, and then it goes back into your assembly code again. You can print R0, info R. You can see what the different values are. You guys understand? And so by doing this, you can kind of step through your code and see what's happening. Okay, so I'll type up a little guide for you guys on how to do this. Okay, and I'll put that on. I'll put it on Canvas. Okay, so that should help you guys with that'll help you guys with your assembly coding, because everything we've been doing so far is simple enough that you could just kind of muddle your way through it. Especially if you use like a helper function, like I think for ASAN if we had did we not have any helper functions to print things? I guess not. Yeah, but for some of the examples at least, there's been print int and things like for FizzBuzz, you could call print int and just see what the values of things are. Might help a bit. Yeah, I mean you don't need it if your code's working right, I guess, but being able to see a line of code at a time run and then look at the values and see them, and there's far more than that. Like for example, GDB has what's called a text user interface mode, TUI, TUI, and you can actually have all the values of the registers up on the screen, or variables up on the screen if you're in C code, and you can step through it and you can look at the variables, and you step through it and look at the variables. So you don't have to print them every time, you just have it up. There's a lot of cool stuff you can do with GDB. It's a very, very well-engineered tool. But what I showed you is just like the basics of it. So breakpoint on a function call, that'll stop at the beginning of your function, and then you step one line at a time, and you can print the register variables and see if it's working. Okay. Quit anyway, yes or no? Please answer yes or no. Do you like me? Yes or no? GDB requires some knowledge of assembly. I mean, not really. You know, GDB is very commonly used in C++ development, right? You can, because it'll, you know, if you GDB a.out, break main, and then step, it'll run. And then you step, it'll, you know, this is, you don't need assembly for this, right? And so, oh, I stepped into the call, right? Okay. So, yeah, you can just step through your C++ code as well. In general, though, ASAN will handle the crashing side of things, and cout will handle the informational side of things. But yeah, a lot of C++ professors teach GDB second semester. I usually do, actually. I just didn't do it last year, so sucks for you guys. All right, so it's my bad, actually. To check registers, yeah, but when you're debugging C code, you can just print the values of the variables. Okay, so let's. Was that useful for you guys? Like as the programs get more complicated, I think that's going to be helpful. And like I said, I'll type up a little guide and put it on Canvas for you. A lot of untaught GDB. Yeah, normally I teach it in 41. I just didn't do it last year, unfortunately. I have a whole lecture on it and everything. I don't think you started recording. Hate for you to have to re-record. It is currently recording right now. All right, so we need to talk about a little bit more architecture stuff, and then we also need to talk about memory accesses. We'll probably do both those today. And for your next homework assignment, I'll think about that. Okay. Let me do a little architecture first. Guess who's doing linked list? We should do linked list in assembly. That would be fun. We will do classes eventually. Classes are actually not as hard as you might think they are. A class works just like an array, but we haven't learned arrays yet, so let's learn arrays. Okay. So, let's say you have a, let's start with a 1D array. Okay. Int R 100. So this allocates 400 bytes of RAM, right? And so this will be on the stack, right? Because we're not doing new or malloc. If we did new or malloc, that'd be allocated off the heap. As it is, this is allocated off the stack. It's small enough; it's not going to cause any problems. And so what happens is that you've got, if we look at the memory map, every time you call a function, there's something called the stack pointer, and when you call this function, the stack pointer is going to move down 400 bytes. Actually, a little bit more because there's going to be other variables and the return address and stuff like that. But we'll just simplify and say the stack pointer moves down to here, and then this R is actually basically an int pointer, right? Technically, the type of an array and the type of a pointer are not the same thing, but the second you sneeze on an array in C, it turns into a pointer. So if you pass it to a function, it decays into a pointer. If you ask it its type, it decays into a pointer. Like if you, I'm a pointer now. Okay. So basically, int pointer R equals R2 equals R. This works fine, right? And all a pointer is a integer, right? On a 32-bit system, it's a 32-bit integer. On a 64-bit system, it's a 64-bit integer. And so this will be set to the beginning of the block of memory, right? Whatever the lowest part of that memory is. And so R would be set to be here, and the stack pointer would also be set to there. Okay. So yeah, like technically there is a type called int array, but anytime you do anything with it, it turns into an int pointer. The only difference is in the function scope that you used it, you could get how big this array is. So inside of the function scope, inside of the scope that made this guy, you can actually find out that it has 100 elements in it. But if you ever pass it to another function, then it turns into a pointer and it loses the size information, which makes the size information completely pointless, because if you're within the function, you know that it's 100 because you just said so right there, right? And that's probably going to be a constant anyway, if you're doing it properly. So R is just going to be pointing at the beginning of a chunk of memory. And so let's draw it horizontally as we usually do for arrays. And I'm not going to draw all 100, but R is going to be basically the same memory address as array element 0. So if you output the address of array element 0, or you output R, like if you just literally did cout R, or if you couted the address of memory element 0, these are going to be the same thing. Okay. So so a pointer to the beginning of this big array is the same thing as a pointer to the first element in the array. Do you guys understand? So that's the address of operator. We don't usually do this, but if you wanted to confirm that a pointer is the same thing as the memory address of the first element, you could do that if you wanted. Do you guys understand? Like array element, this is array element 0, right? Here. So the memory address of it is the same as the pointer. Okay, so typically when we do memory accesses, we talk about base plus offset. That's the typical way we do it. Or you can just have an iterator go down it. So for example, if you wanted, you could say r plus equals 1. This is called pointer math. And what this would do is it would take r and it would move r to be pointing at element 1 now. So this does not move it, this moves it 4 bytes. 4 bytes to the right. It doesn't move it 1 byte to the right. This is something that students get wrong a lot. In C++, if you add 1 to a pointer, that means move 1 array element to the right. In assembly, it would move 1 byte to the right. Okay? Like in your code for pulling characters out of the string, when you added 1 to the offset, it is 1 byte to the right and it grabs you the next character. In C++, if you add 1 to a pointer, then it points to the next element in the array. So it goes from pointing to element 0 to pointing to element 1. Every int is 4 bytes, right? So it didn't move a quarter of an int to the right, it moved 4 bytes to the right. And that's why this type information here is so important in C++. That's why you need to know what you are a pointer to. If this was a double pointer and you said array plus equals 1, then it would move 8 bytes to the right. Okay. In 32 bytes, it would add 8. No, because even though the pointer is a 64-bit number, it's still pointing to integers. And so integers are 32 bits, more or less standardized these days. You'd have to go and find a really obscure system, old system that has 16-bit integers. So it moves a number of bytes to the right equal to the size of int, right? And so this could easily be a 64-bit number, but it moves 4 bytes to the right every time because it's pointing to ints. If this was a char pointer, if that was a char pointer, then every time you move the pointer 1 to the right, it would move 1 byte to the right because it's a char pointer. Okay. And so in C++, when you do pointer math, it's actually based on how big the type size is. And that's why you need to know, am I an int pointer, am I a double pointer, am I a float pointer, am I a char pointer, am I a short pointer, that kind of stuff. For classes, it could be pretty large, sure, yeah. You can easily have a class that is 100 bytes, whatever, you know. And then it would move 100 bytes to the right every time you incremented a pointer. Right? And so you could be like, where's my mouse? You could be like R++. That's pretty common too. So if you have a pointer and you go ++ on it, it points to the next element of the array. Okay, so base plus offset. So one way you can iterate across an array is just by having a pointer and going ++, ++, ++, ++, until you hit the end. End can be indicated either by a null byte if you're doing a string, or there could be an end pointer. End usually points 1 off the edge of the array. And then you just check to see if your pointer matches end. If your pointer matches end, you're at the end, you bail out. Strings are null terminated. Or you can have, like, you know, just the size, right? And the size would just be like how big this thing is, right? So there's different ways of knowing when you've gone to the end of the array. Array minus equals minus minus 1 plus plus. Right. So you do pointer tricks, or you can do base plus offset, and base plus offset would look like this: array square bracket I. Right, and so this is what we call the base, which is the pointer to the beginning. Right, it's the pointer to the beginning of the array. So we're not moving it now. So when you do base plus offset, you usually don't move the base. What happens is the offset will increase. And this is called the offset. Okay. And so those are two different ways you can access an array. You can either have one pointer or an iterator that just goes through it, or you do base plus offset, so the base stays the same, which is r, the pointer to the beginner, and then the offset is I, and it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. And so when you do r square bracket I, that actually translates directly into this, right? Load, and this is an integer array, so it's going to be LDR, not LDRB. Load into register 6 from register 5 plus register 4, whatever, you know, and that would be R, that would be I. So C will actually translate that array access directly into that assembly code. Okay, and R6 again, it could be any register. I'm just picking a number at random, right? So if we say X is equal to R square bracket I, then I'm just arbitrarily calling X to be R6. Do you guys understand? So R is the starting point of the array, and then I is the offset into it. The only difference here is that R4 should be equal to I times 4. Why? For your code, I and R4 were the same thing. You just added 1 every time. Why do we need to add 4 every time when we're reading through an integer array? Like if we're going to be loading ints, why do we need to add 4 to R4 every time? Why not 1? Is it 4 bits or 4 bytes? 4 bytes, yeah. So basically, if you were to do this in assembly, R would stay the same. You'd load an integer out of it like this, and then you would add 4 to R4. You'd add 4 to R4 because it's 4 bytes at a time you're loading. When you do LDR, it loads 4 bytes. Okay, and that would be how you would write a for loop in assembly to read from an integer array. That's why I started you guys with a string. A string is, LDRB is actually easier to work with because you just add 1 every time, and that's 1 byte to the right, and you load it, and 1 byte to the right, and you load it. And so, do you guys understand this? Base plus offset? Like, it sounds maybe more complicated than it is. You have a pointer, and then you have a offset from that pointer. Would this compile in C++? I is an integer, R is a pointer. Would this compile in C++? Could you switch the R and the I? R. Could you switch the R and the I in C or C++? The answer is yes. You actually could. You actually could do that. So you actually 100%. Yep. I will show it to you. All right. So vim main.cc. Look, it's already set up. Let's just do this. Did you guys see this monstrosity that I did right there? Compiles just fine. Element 5 is 5. Element 1 is 1. Works just fine. It looks absolutely hideous, right? You're using the loop counter as the array, and you're using the pointer as the offset, but technically it just adds the two of them together, right? And so addition is, you know, commutative, distributive, and you know, and so technically that horrible monstrosity actually works. And you will confuse the bloody hell out of anybody who tries reading your code after you. This doesn't work with vectors, by the way. So if you try doing this with a vector, vector events and vec of size 10, all of which are initialized to 5. If you tried saying vector 4 equals 4, that's fine. But if you tried saying 4 vec equals 4, that is not fine. So if you try compiling that, this line does not work. And the reason why it doesn't work is because this is actually an overloaded operator. And so they have overloaded the square bracket operator for vectors so that it will pretend to be an array. It's not, it's just a class, but it's got the square bracket operator overloaded on it. And so this will pretend to be an array and it'll access element 4. They have not, however, overloaded it such that the vector appears on the right-hand side of the square bracket operator and an integer appears on the left-hand side. Apparently that was not a pressing concern for the C++ community. So vectors are not actually drop-in compatible for arrays, because arrays, you can do this hideous, horrible monstrosity of a syntax, and it does not work with vectors, unfortunately. So yeah. Also, you can't have a variable named 4. So let's just verify that this works. There we go. So they did not make an operator square bracket overload for the integer on the left hand side. Just probably good design, honestly. Doesn't work with a vector. It does work with an array. Okay. So the reason why this works, though, is because C++ will just very happily add the numbers together. That's all it's doing. It's just, square bracket is just it's the equivalent of this. Dereference array plus I. That's all the square bracket operator does. So now it adds the two together and then gives you the variable at that address. And it does not care if you do that or if you do that. Either way that works. It's just, the square bracket operator is just syntactic sugar that just does that for you. But because the square bracket operator is not overloaded for vectors, it doesn't work with vectors. It's job security right there. Nope. Nobody understands you, nobody can fire you. Okay. And there a lot of organizations have somebody like that they've written such dark and deep and mysterious code that they literally can't be fired or replaced because they keep the company running and nobody can fix their code because they write horrible, horrible things like this. Okay. Okay, so yeah, and so basically if you were to do this, then it would just switch the R4 and the R5, right? And that's fine. Final use of function pointers. Yeah, function pointers are not too bad. Okay, so let's talk about two-dimensional arrays. So, two-dimensional array. Next step is write bad documentation. Why write bad documentation when you can write no documentation? Or, I don't know. Yeah, I guess bad documentation is even better because it throws people off the scent of what your code's actually doing. 3, 4. So I'm going to make a little 5x5 array here. Let's see how good I can freehand this. 2, 3, 4. Reasonably decent. Okay, so this is row 0, row 1, column 0, column 1, 2, 3, 4, row 0, row 1, row 2, row 3, row 4. Okay, so this may come as a surprise to you guys, but there are no such thing as 2D arrays in memory. In RAM, everything, especially if you make an array like this, array, let's make it an int array 5 square bracket 5 like that. This is going to make a 5x5 array. But it actually just, this is actually the same thing kind of as just being like int R25, right? These two things are different types technically because it's a 2D array type, but it basically does the same thing, right? And so everything in memory is just in memory. Like there's no 2D RAM or whatever. Regexes are another great source of job security, yes. So this is more or less what it's doing. And in fact, usually a lot of times when I do 2D arrays, I actually just make a 1D array because then I don't have to worry about anything. So yeah, so these two things are the same. But here's the question. Who is next to who in RAM? Who is next to who in RAM? So there's something called row major ordering. And this is our topic for today. And so what that means is who is first in memory, who's last in memory. So the first guy in memory is this one. This is the first, and this is the last. Okay. But does memory, is this guy next to this guy in memory, or is this guy next to this guy in memory? Which one of these two people? If this guy is memory address, I don't know, 5,000 here. If R is equal to 5,000, who's that address 5,004? Right? Because remember, everything is 4 bytes apart when you have an integer array. Right? We're talking about an integer array. So which one of these two people is at 5,004? Is it row 0, column 1, row 0, column 1, or is it row 1, column 0? Who is at 5,004? 2D arrays are fake, and it's actually just a straight line. Yeah, literally, it's going to lay out the thing like this. It's when you do a 5 by 5 array, it's making a 25 array. Okay. Yeah, row 0, column 1. Very good. This is the next person. This person here is at 5,004. This one is at 5,008, 5,012, 5,016, and then this guy is at 5,020. So this is all contiguous in memory this way, and then it wraps around and it goes this way, and then it wraps around and goes this way. It's like reading a book. Okay, so this guy here is adjacent to this guy here in memory, and this guy here. Okay, so these two fellows are next to each other in RAM. Okay. It's called row major ordering, and most sane programming languages do this. I think Fortran was originally column major, and I think it has an option now for being either column major or row major. I'm not really a Fortran guy, so don't quote me on that. But yeah, Fortran, I believed, originally went down like this, but C kind of took over the world, and so C mandated row major ordering, and so I think Fortran has the option of it now. Okay, so yeah, so how do you access, let's say, this person? Let's say you're writing assembly code. Okay? And you will be. Not for your next one. Your next one's going to be just a fun assignment. But this is maybe 2 assignments from now. We'll see. So the base is 5,000, right? And so that would be passed in. So like, let's say we passed your assembly function R. R is the base. Base, we'll just say, is at memory address 5,000. Okay? And you want to access column 4, row 3. Row 3, column 4. What is the memory address for this bad Oscar right here? What is his memory address? How do you figure that out? LDR R019. Let's see. So that'd be 0, 1, 2, 3, 4. 4 plus 5 is 9. 9 plus 4 is 14. 19. I like the spirit developed, but it's not accurate. So DeBella did figure out that this is essentially R. We're basically talking about R19. So this is the 19th element in this 2D array. Okay. Anyone? I think Muya has it. Okay. Yeah, so it's 5,000 plus 4 times 19 if you want to do it that way. It's the 19th element, so you multiply it by 4 because these are integers. They're 4 bytes to the right. And so this is the offset, or base is 5,000, and then the offset is this, right? So the base is 5,000, 5,000 plus the offset of 19 elements to the right. Each element is 4 bytes, so it's 4 times 19 bytes to the right of 5,000. Okay. And so that would be 5076, right? Is the memory address. So the memory address of this guy is 5076. So what is the general equation for this? Well, the general equation for this is you take the row. So every time you go down a row, you move 5 elements to the right. You guys see that? So if you go down one row, it's going 1, 2, 3, 4, 5 to the right. If you go down another row, it's another 1, 2, 3, 4, 5 to the right. Okay, so it's going to be the general algebraic equation is row, I'll do it in C++ style, row times row size, and then every time you move 1 to the right in the columns, it's 1 to the right plus columns. And that's how many elements to the right you are times the size of the size of int. Okay. So remember, it's not guaranteed to be 4 bytes, right? So the actual memory, the memory of array row column is equal to 5,000, which is R, plus row times the row size, plus column quantity times the size of an integer. Does that hurt your head? Is it too easy or too hard? If R0 is 5,000, 19 times size, 19 times size would be the offset, right? So 19 times the size of an int in this case is 4. So 19 times 4 would be the offset. So 5,000 would be the base. 19 times 4, 76 would be the offset. So the actual memory address you're going to load from is 5,076. Okay. So in assembly, you would probably do something like this. You would load LDR, load into, I don't know, register 10, I don't know, whatever value we're loading from. So if we're doing like int x, if we're doing like int x is equal to r 3 through 4. Or is that backwards? Yeah. 3, 4. Then we're going to load from RDR. We're going to load x. In this case, would be R10. Just randomly assigning it from R. Let's say is just an R5, and that would be the base. And R6 would be the offset. And so R5 would be like 5,000 or something like that. The offset would be 76. And so that would load from memory address 5076 into X. That's what the code would look like in assembly. And then that's usually passed to you by a pointer, right? So you have your function call, it takes that in, and so you just move R0 into R5, so you save it. And then this is going to be your counter, and so that's like your I kind of thing, right? So you're going to start off with I equal to 0, and then every time you go through a loop, you're going to be like add R6 4, right? And then you'll just sit there and do this command over and over again, loading one integer at a time. Each time you add 4 to R6 until you get to the end of the array. And that's how you would do your assembly code. So to read from a 2D array, you basically just, you start off by putting 0 to R6, and then you do your loop, and then you add 4 to it, and then check to see, do some sort of comparison against the end, and then jump back up to, no, not to here, to the top of the loop. I don't know if that's clear or not. So before the top of the loop, you'd have like a top label here. And you initialize it to 0, and then you go through the loop. Every time you finish the loop, you add 4 to it, and then you do a comparison of R6 versus the end. You might even save that into a register, right? You might actually save the ending address into the register, and if it's branch if less than or equal to top, and then it'll come back up here and do that again, and you can just iterate across an entire 2D array that way. It's actually just the same thing as iterating across a 1D array. But if you ever need to grab the person above you, grab the person below you, then you need to know this algebra. Okay? And so the algebra, I will actually type in text for you. Click. It's really small text, isn't it? Can I make it bigger? Yes, I can. Offset is equal to row times row size plus column. That's the index number, and then the index. And the offset is then index times the size of init, if we're doing ints. Excuse me. Okay, so now what if you're doing a 3D array? What if you're doing a 3D array? How does the algebra work for that? How does that work? 3D array. Like you're doing image processing, right? X, Y, and then you've got a red plane, a green plane, and a blue plane. It's a 3D array. So if you're doing image processing, which you probably will, there's basically 1, 2, 3, 4, 1, 2, 3, 4. I even got all the colors, right? Okay. 1, 2, 3, 4, 1, 2, 3, 4. So when you have an image, sometimes images are held interlaced, which means it goes RGB, 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 RGB. But in the way that we've been doing in this class, all the reds are together, and then after you finish a 2D array of all the reds, then it goes into a 2D section of all the greens. Then after you read through all that, then it goes through a 2D section of all the blues. And so if you want to go down, it's like if you're here, and you want to know what the green value is here, then you add row times column, the number of rows times the number of columns. Do this in a different color. So like let's say you're here and you want to grab the green value here and you want to grab the blue value here. Because like let's say you want to grayscale it, right? So to grayscale an image, what you do is you say grab the R value at row and column, grab the green value at row and column, grab the blue value at the row and column, and then you add them together, right? You add R plus G plus B divided by 3, and that will give you the grayscale value. And then you write that result here, here, and here, and then you've got that will convert a color image into a grayscale image. Basically, at every pixel, you average the red, green, and blue together, and then write that back into the red, green, and blue channels. So, so if you're currently here, right? If you're currently at this place here, and you want to access this person here, you have to move how many? Let's say these are integers. Usually they're unsigned shards, but whatever. Let's say you want to move down to here and read that value, and then move down to here and read that value. So your current index is, let's call it index. And so to get the green value, you're going to add rows times columns to it. So the number of rows is 5, number of columns is 5. So you add 25 to the index, and that moves 25 ints to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17, 18, 19, 20, 21, 22, 23, 24, 25. So 25 ints to the right will give you the green value, and then 25 ints to the right of that is going to be the blue value. So index plus, it's not, it's a plus, it's supposed to be a plus. And, oh, it's an x, index plus. Oh, there's the plus. Okay. Get a thicker pen, maybe. There we go. Index plus 2 times rows plus columns. Now it's like spray paint or something. Okay, so it'd be index plus array size for each separate value. Index plus one of the 2D arrays, yeah. So you'd to go to the next 2D array, you figure out how many elements are in this 2D array, and then you go, so there's 25 in this one, right? It's a 5 by 5 array, right? It's 5 by 5. And so you go 25 elements down, and that gives you the same person. In the green plane, you go 25 elements down, it gives you the same person in the blue plane. And so it's usually a good idea to just sketch these things out, like what I'm doing here. And you know, don't do like 100 by 100, but like 5 by 5. And then you can actually just sit there and count if you ever get stuck. Like, all right, 1, 2, 3, you know, you'd sit there and count. Okay, it's 25 below me. Okay. And then this guy is, you know, as long as you remember row major order, which means you're reading like a book, right? This is row major order. As long as you can remember that, then the person to the right is 1 index to the right of me. The person to my left is 1 index to the left of me. The person above me is 1 row above me. 1 row is 5. And so this guy is 5 below me, and this guy is 5 above me. Okay. And so it usually helps to just sketch it out on paper, and then you can just count, like, okay, 1, 2, 3, 4, 5. Okay, so the person below me here is 1, 2, 3, 4, 5 higher. The index is 5 higher. 1, 2, 3, 3, 4, 5. Okay. Top left is the beginning. The base is the top left corner. 0, 0, 0 is always the beginning of the array. Computer science, 0, 0 is usually the top left. Okay. And so the overall algebraic equation for accessing a 3D a spot in a 3D array. And so this is, like I said, I do this a lot, right, in my code, where I just make it 1D array. And then I'll have a helper function that will convert, it'll project from 3 dimensions into 1 dimension, or however you want to call it. But basically it'll do the algebra. And I do this because it's a lot easier to just pass a vector, you know, rather than having a vector of vectors and a vector of vector of vectors. I just make a vector, right? So if I wanted to make a 5 by 5 by 5 vector, I just make a vector of size 125, right? and then I just pass a single vector around, and then when I access it, I just do the algebra, or I have a helper function that does the algebra for me. And so the algebra, so if I wanted to access this person here, and I wanted to find out what his index is in a 1D array, like let's say I have an int R125. It's a no, wait, it's not a 5 by 5 by 5. It's a 5 by 5 by 3. This is a 75, like that. If I wanted to find out what index this person is, he is column 3, rows 3, and plane 2. So the index is going to be equal to, we're 2 planes down, so it's 2 times row times column, which is 25, right? So we're 2 planes down, so we're 50 down from the beginning, and then we are on the 3rd row, 3 times the row size, which is 5, plus 3 to the right. And so the total index we're at here is 50, 65 plus 3, 68. Okay. So we're on index 68 out of 74. Okay. If there's 75 elements, the very last person here would be 74. 68, 69, 70, 71, 72, 73, 74. Right? You can actually just count it out to just verify that you're doing the math right. So picking a spot like this near the end is a good thing, because you just count backwards and just make sure you're doing the math right. I probably wouldn't pick 3 and 3 just to make sure that I didn't get the row and column backwards. Right? So questions about this? Is this too easy, or is this too hard? Or is it just right? If you're doing this in assembly, the offset would be equal to 4 times 68, right? Because it's integers. So it'd be 240 plus 32, 272 bytes to the right of the base. So the base was at, if R was at 5,000, then this guy down here would be at 5,000 and 240, 272. Okay. So if the base of the array was at 5,000, then this guy's memory address would be 5,272. There's 68 elements to the right. Each element is 4 bytes. It's just a lot of algebra, and it's easy to get the algebra mixed up in your head. That's why I'm saying it's a really good idea to just sketch it out and just be like, all right, if this guy's at memory address 5,000, then this guy's at memory address 5,004. It's 4 bytes per integer. This guy's at memory address 5,008, right? And yeah, this guy's 5 elements above me, so he's 20 bytes above me, 20 bytes below me. Can you show us an example in code? Yeah. Not bits, bytes. It's 4 bytes, not 4 bits. 4 bits is a nibble. It's a half byte. Can we stick to using LDRB? No, because if you're loading an integer, you need to get all 4 bytes at a time, right? If you do LDRB, then you will get 1 byte out of the integer. And I mean, I guess you could like do bit shifting and masking and throw it into. It's way too much effort. Use LDR. Use LDR. So let's see here. Const. How many rows do you want? Algebra. How many rows do you guys want? Somebody toss out a number. 5. Okay. How many columns do you want? Don't say 5. We'll do it. 32, 14. All right. And how many planes do you guys want? 6. All right. All right. So we are going to make an integer array of. Let's see. Planes, rows, columns. I think that's right. Okay. I don't actually like doing that. I tend to do this. Actually prefer doing it that way. Because then it's just a 1D array, and it's a lot easier to just pass 1D arrays to things. Because that's all it is behind the scenes. Alright, so what should we do with this? So this is how many integers there are total in size. Front I equals 0. I is less than size, I plus plus. R I equals R2 I equals 10 times I. So element 0 is going to be set to 0, element 1 is going to be set to 10, element 2 is going to be set to 20. Okay. And then we will the function void ASAN R passing in pointer. Are we in C++ right now? We are. So extern C. Okay, you guys understand? And so I am going to then pass. Just not even going to worry about this one. I'm going to pass R to it, ASAN R. And then I'm going to print out all the elements. It's going to be a lot of printing out, isn't it? All right, so we're going to print out each I times planes, no, not planes, I times rows times I times rows times columns plus J times columns plus K. That's the algebra right there. Then at the end of the row, it will see out a new line, and then after it finishes printing a plane, I'll print out some separator, something like that. Okay. So, yeah, okay. I changed planes, did I? Did I do something wrong? So this would be the 1D away, 1D away, 1D way, 1D, 1D way of accessing an array. Jeez, that's a tongue twister. It's the 1D way of accessing an array is like that, and then this would be the 3D way of accessing an array. I sound like Elmer Fudd. That's the way you access an array, or an array. Okay. I went from 6 planes to 3. Yeah. I just don't want it to spam too much on the screen. 14 by 5 and 3 of those sounds about right to me. Okay, so do you know the way? Okay, so let's start off actually by just not calling this function at all, and let's just verify that our array is getting set up right. So G++ main.cc, comparison of signed integer. Yeah, you're absolutely right. Size t here. Size t is G++ main.cc. You don't want to compare signed and unsigned integers as a general rule. Okay, so there's our array. I could probably there we go. Lined up nice. Lined up very nicely now. Did you guys see how I did that? Like that. So there is the IO manip library, which isn't, I guess, really that important because who uses cout for reals. But yeah, set W sets the minimum width of the next thing that's printed. And so I'm setting the width of it to 4. And so if there's a fill character, in this case, the fill character is space. And so if it's not 4 characters long, then it fills in spaces, so everything lines up nicely. And so you can see this is our array, right? So the first plane of the array goes from 0 to 690, nice. And then the next plane has these numbers, and then the next plane has these numbers, and that is our array. Now, and what about itman, IO itman? Nice. I only saw the original itman, but that was pretty good. Donnie Yen is a fantastic actor. This guy. So, yeah, it's a good movie. 20 million, is that it? Rogue One, yeah. Yeah, I like that movie too. All right. Okay, so that is how I do multidimensional arrays in C++. I don't actually like doing that because, like I said, it's a lot easier. Like the types of 1D arrays are just easier. And if you need to, like if you can't remember how to do that, then you can write a helper function, right? It should be like size t index taking in size ti, let's see what would that be, plane, size t, row, size size t column, and I would probably want this to be inlined. Again, the inline keyword isn't binding, but it does indicate to the compiler what you want to do. So if we're on plane, okay, so the int return value is equal, probably don't need that actually. We're just going to return what plane we're on. So if we're on plane, if we've gone down one plane, then we've gone down row times column and indices. Right? If we go from one plane to the next plane, we've gone down, in this case, 5 times 5 elements. Right? So every plane we go down is row times column elements down. And then every row we go down, there are 5 columns per row. And so, we don't know what these values are. I'll do a bad. Here we go. And so every time we go down a row, we've moved 14 elements to the right, in this case, because we have 14 columns. So every time we go down a row, we've moved 14 elements to the right. You guys understand that? So like, in this case, we have 5 columns. So if you go from here to here, it's 1, 2, 3, 4, 5. So the number of columns is how many people we move down. Why size t? Because indices into vectors and arrays are size t. That's the appropriate type for them. So anything that goes inside of square brackets like that should be of type size underscore t. And that is on our system here, it is a unsigned 32-bit number. On the other server, it's an unsigned 64-bit number. And basically, it is a number large enough that you can index any array element using it. It's a bad idea to use int. You can use int, but what happens if you access element -5 from an array? It's a bad idea. Right, so plane times rows times columns. So every time we go down a plane, we've moved rows times columns to the right. Every time we go down a row, we have moved number of columns to the right, and then every time we move right a column, if we move from here to here, we've moved 1 to the right. Okay. So and then if this is the algebra, right? And when I was in your shoes, I always did it wrong. Like I'd multiply row times rows and plane times planes and things like that, and the algebra never worked out right. And so I eventually just I've done this so many times. This should be correct, right? Right, and it helps if you just look at a picture, right? Every time you go down a plane, you've moved rows times columns to the right. All right, so then you can access it by just doing this. So inside of the square brackets, you can put the helper function index ijk, like that, and then that makes accessing the array human readable. You know, most experienced computer science people have done this enough times, they will recognize what you're doing, but that's probably more readable, right? It's probably more readable. And the compiler probably should optimize that away so it does the same thing. You can always put it into Godbolt and see if it is doing the same thing. And you can see that our code is the same as before. Okay. Yeah, anytime anything goes into square brackets, anything goes into .at, it should be of type size underscore t. You can use an int. The language oftentimes will complain at you because you can't have negative numbers into .at or square brackets, right? It's guaranteed to be bad, right, if you use a negative number. So if you use unsigned, then if you do get a negative number, it wraps around to be really big, and you can only do you only need 1 bounds check instead of 2, right? Size underscore t is an unsigned 64-bit on the server, on the main server. On this one, it's an unsigned 32-bit. Actually, let's find out. Let's find out. Maybe I'm just guessing, because I am just guessing. What is the size of a size t here? Four bytes. Okay. And then if I were to go onto the other server, nope, wrong server. Go onto the other server. See what is the size of a size key, and hell, let's print out what the size of a pointer is too. Size of a linked list pointer. You'll see that on a 64-bit system, they are 64 bits. On a 32-bit system, they are 32 bits, or 4 bytes. Okay. So size t scales to match whatever the memory size of the system is. Okay. So we're on a 32-bit operating system here on the Raspberry Pi, so it's 4 bytes. And yeah, so it's an integer whose size can address all of memory. That's one way of thinking of it. And so it doesn't have anything to do with the size of integer. It has everything to do with the size of a pointer, actually. So, okay. So let's write a assembly program that will add one. It'll add one to every element in this array. And so we're going to need to pass in another value, and that is the. Let's do this. Let's do it cleverly. End. Let's pass in an end pointer. Because this is how C++ works a lot of the times. With C++, you pass in a pointer to the beginning of the range that you want to do an operation on. And then you pass in a pointer to the end. And the end is usually one past the end of the array. Right? If you're doing the whole array, start, or R, is the beginning of the array, and end is one element past the end of the array, usually. If you're doing if you're using some other container like a linked list or a binary search tree, then end will be an iterator pointing at a special sentinel value that when you detect that you're there, you terminate the loop. But for some contiguous memory like a vector or an array, you do it like this. So this will be a good experiment. Okay, so let's do this. Actually, let's do it before and after. Let's do it before and after. So cout before, mark x, mx, y single quote x will block copy, key to paste. After, and then it's going to print the array again. So we need to write this person here. So I could do this in inline assembly, but I'm not. So it's called ASAN. And notice how I don't have the curly braces here, right? Like what I showed you guys before, I did it like this, right? But that's not needed. Like with most things in C++, curly braces aren't needed if you have one line. So then ASAN r.s. And then I always like to paste the C signature of my code in assembly, so I know what the hell I'm doing. Right. So global ASAN r. All right. So is Dolio still here? Dolio, where is R going to be passed in? Which register is holding R? Which register has R in it? R0, good. And Trangio, which register is going to have the memory address for end? Ooh, I'm not calling this properly. While you're answering that, let me call it properly. So it's R plus planes plus times rows times columns. Okay, that's right. Okay. R2, that is incorrect. This is R0, so this guy is our Trangio. End is going to be in R1. It's in R1. So the first parameter is passed in R0. The second parameter is passed in R1. It would be R2 if we were passing 64-bit numbers. 64-bit numbers would get passed in. This guy would get passed in R0 and R1. This guy would get passed in R2 and R3. But this guy is R0. This guy is R1. So the first thing I'm going to do in this is I'm going to back up my pointers because R0 and R1 are hostile territory. They're hot. They don't stick around very long. I don't know if I'm actually going to call a function. Maybe I don't care. Do I care? Maybe I don't care. Maybe I don't care at all. But it's always a good habit to get into. So I'm going to move R4, R0, move R5, R1. So save R into R4, save N into R5. Okay. All right. So then, do we need a loop counter? No, we don't. So we'll just do this. Top of the loop. LDR, this is a 32-bit load. LDRB is 1 byte. LDR is 32 bits. It's a whole word. 32 bits is a word. Word. Dave Chappelle says. So we're going to load 32 bits from R. Okay. So we're going to load 32 bits from R. So we're going to load into register 6, let's say, from register 4. Int x is equal to r square bracket 0, let's say. And maybe this, I haven't actually said what this function is going to do, did I? Let's just add 1 to everything. Let's just add 1 to all the values in the array. Okay. So let's just add 1 to the value. And then let's store it right back. Store R6 right back into R4. And does that work? I think that might work. It's been a while since I've used right back. Let's not worry about that for now. So so int x plus plus, and then array element 0 is equal to x. And then we're just going to add, I think if you use the exclamation mark, we don't even need to do this, but it's been a while since I've looked at that syntax. So I'm just going to add 4 to the pointer. R++. So I'm actually going to move the pointer to the next element in the array. Like I said, I don't even need a loop iterator, right? And so let's see here. And then we need to compare R4 and R5. Is R greater than or equal to the end? Branch if less than to the top. And oh, we need to do our pushes and pops, right? Just gonna copy and paste this. Unfortunately, I don't need that. Okay. And technically, we don't need to save all these different registers also. Technically, we could just use R0 and R1 as well, but I don't care. All right. So let's try this. G++ ASAN r.s and main.cc. Run it, and look at this. Right? So code before had 690 there, code after 691, code before had 130, code after has 131, code before had 1660, code afterwards has 1661. Cool. R4 to R12. R12 is a scratch register, and so R12 actually isn't preserved like in the same way that R0 to R3 are not preserved. So there's no reason backing up R12. You might see me doing that in some of my functions, but that was a typo. Yeah, some of my code you might see me do that, but it's a typo. Our R12 is called the scratch register, and so basically it is not preserved, guaranteed. So you can preserve it if you want. It doesn't hurt you, but if you think it's preserved, like if you do a branch with link, it's not going to be preserved. And so I've gotten out of the habit of doing that because there's no point, for one thing, and for the other, it makes you think that you're safe. But in reality, you've got 8 registers that are safe. 4, 5, 6, 7, 8, 9, 10, 11. There's 8 registers that are safe between BL. When you do BL, R0 through R3 are wiped out, R12 is wiped out, 13, 14, and 15 you should just kind of not touch. So you've got 8 registers, 8 general purpose registers to work with, and that's usually pretty good. If you need more, you can access memory and stuff like that. But okay, so this code here is working. So let me see if that write back. See if that write back. Let me see if this works. Nope. Let's see. Nope. Yeah, I don't remember the syntax for it. But basically, you can combine these 2 lines together using the exclamation mark. The exclamation mark will say, you know, read or write to this address in memory, and then move the pointer also. So rather than you having to move the pointer manually like this, you can use the exclamation mark to move it for you. And I just am blanking on the syntax right now. It's in your textbook if you want to save yourself a add, basically. So do you guys understand this? What's going on here? So basically, I don't even need these technically, but again, it's a good habit to get into. Don't rely on R0 and R1, because you put in a debug call, you know, print int, and then your arrays are erased, you know. So just get into the habit of never using R0 and R1, except when you're passing things to a function and getting things out of a function. Homework assignment is this easy. So yeah, let's talk about your next homework assignment. You said LDR is 32 bits. It is. It is. It's reading an entire integer. Okay. Any questions about that, Walker? Okay. Yeah. So this homework assignment, this program takes in a pointer to the beginning of a 2D array, takes in a pointer to the one past the end of the array, which is, I'm doing it this way because this is how C++ does it, right? And basically, I just am moving the point. I load from the pointer, I add 1 to the value there, and then I write it back into the pointer, and then I just move the pointer 4 bytes to the right, just 32 bits to the right, because it's ints. We're doing integers here. So I move it 4 bytes to the right, see if we're at the end. If we're not at the end yet, then we advance, and we just keep doing this over and over again. Okay. This is a very common pattern. You know, you don't have to have a separate variable for I, you know, to do the offset. It's very common to just advance a pointer through memory until it hits a guardian value. Okay, yeah, so let's talk about the next homework assignment. No rights / change. I could put this into the demo code, I guess. Let's see here. Move ASAN R into C-Sky, homework, ASAN demos. I've already got one for arrays, huh? Yeah. I'll call this 12.5 2D arrays.s. Move main.cc into sysky homework ASAN demos 12.5 main.cc. Sudo deploy homework to CSI45 class, ASAN demos, no clobber. Okay, so you guys will be able to view my wonderful source code in the 12-5 section. That one's actually pretty different, actually. CD ASAN demos vim 12 arrays. So this one actually shows you how to make an array in assembly, which is a different thing. So this is something we haven't talked about yet, but there's a data section where you can make, this makes 400 bytes of memory. And so rather than getting it passed to you by C or C++, you can actually make an array of 100 integers, right? So. All right, so we are going to do locksmith as our next assignment. So one of the most useful things, chmod, why is everything executable? Make clean. Move. Okay, one of the most common uses of assembly, because a common question I get is like, when are we ever going to use this, right? When are we ever going to use assembly in our professional programming lives? And the answer is not often. Not often, if you're like a normal programmer. But understanding things like row major ordering, like what we've been talking about for the last hour and a half, really important. Because you need to understand what's next to each other in memory so that you understand cache coherency and things like that. Like understanding the details of how the system works makes you a better programmer just overall. And you can also do things like pass 1D arrays to things instead of relying on 3D arrays, which can get kind of gnarly as far as the types go and stuff like that. So one use, though, of assembly is to remove copyright protection on things, right? So if you everything's executable. Why is everything executable? So for this assignment, you're going to be given a program that's been disassembled. Remember how I showed you in GDB how you can disassemble a program? You can actually do that for like a commercial program, right? And so, for example, I purchased MATLAB, and then the MATLAB people for thousands of dollars, right? MATLAB is not cheap. It was for a project I was working on for my professional business. I purchased MATLAB for thousands of dollars. They sent me a box, and it had my receipt in it, and it had no CD. Like, it didn't come with the DVD that they said was in the DVD packing list, DVD. And I'm like, shaking the box, and it's empty. Apparently, $2,000 doesn't give you enough quality assurance to actually get the damn DVD that you paid for $2,000. Like, Steam's more reliable than the damn MATLAB people. And so what I ended up doing was I had a pirated copy of MATLAB, and so I just ended up using that instead. And I figured if they ever got mad at me, it's like, look, I have a license, you know, what do you want? You know, I own the right to use the software, and you assholes didn't even send me a DVD for, what I paid for it. So pirated versions typically will remove copy protection off of things. And so I paid $2,000 for error. Yeah, I paid $2,000 so they wouldn't sue me, basically. But how would they know anyway, right? But it made me feel better about myself because it was for professional work, and I tend to actually be fairly conscientious when I do things legitimately. And so Yeah, and so anyhow, so let's say that you discover some old software, like Citadel for the Mac Plus, which was a great video game, honestly. One of the most interesting RPGs I've ever played. And it has this stupid copy protection system on it where when you launch the game, it asks you to line up two glyphs, and there's a paper wheel, and you rotate it, and you have to enter the code there. And so let's say you have the executable, but you can't get around this copy protection. Well, you can disassemble it, and you can pull up the assembly for it. This is for a game called Hangman, and it's got, this is an actual C++ program written by a high school kid. So the code's actually kind of garbage. And it's Hangman, but it is, like, it's even got the source code in there. That's amazing. So, and so it's copy protected, right? And so all you have is the assembly, and you have to remove the copy protection. Okay, so this is a very fun assignment. Basically, there's 3 levels of difficulty. There's Locksmith 1, which is easy enough that I think most students should be able to get it. Again, these are decompiled C programs or C++ programs. And so for this one, you'll see it says something like, please enter the password, a number to play the game. And that's at label LC0. You can tell this is generated by a compiler because the labels are like 0, 1, 2, 3, 4, 5. It just goes down the line. And that means memory alignment, so aligned to the 4-byte boundary. So please enter the password to play the game. Password must be a number, goodbye. Enter error, incorrect password, one more try. Password not accepted, goodbye. Password accepted, welcome to the game. So LC5 is the label containing this. This is a string, by the way. And you can see the string ends with a null character. So that's byte 0, right? If you guys remember that from last time. Strings in with a byte 0. Another way you could do this in assembly, by the way, is to say ASCII Z, and then you don't need that. Same thing. Okay, so then here's main. Okay, so what happens if we just make this? Type make, run it, please enter the password, 11, one more try, 11, password not accepted. Please enter the password to play the game, 42. Oh, actually, that is the password. Look at that. Okay, cool. So, who could have guessed? This assignment will essentially teach us the skills to hypothetically download programs for free. No, it will not teach you how to download programs for free, Rivera. It will teach you, after you've downloaded a program, how to remove the copy protection on it, which is a protected activity if done under certain circumstances. So, it's not always illegal. So somewhere within this code, you will see that there is a check. I'm not gonna show you guys where. There is a check for 42 in this code somewhere. Who knows where it is? Somewhere in this code, it's gonna scanf. By the way, is how you read something. It's cin in C. So it's gonna read in a number, and somewhere within this code, it's gonna see if the answer that was read in was 42. And if it was 42, then it will branch to the section of code where it will write to the screen. Put s is the print function. Put string. It's simpler than printf. And so if all you're doing is printing a string, it does put s instead. And so it's going to load memory address L4 plus 24. So let's see if we can find memory address L4. Where is memory address L4? Plus 24, 6 down. 1, 2, 3, 4, 5, 6. LC5 is you. And so LC5 is password accepted. Okay. So this put s down here is, that's going to load the string password accepted, and that prints it to the screen. So LDR loads, this is what we've been doing, right? Loading from a memory address. And so you can actually use labels as a memory address, kind of. And so this is going to load from label L4 plus 24 bytes, 6 down. L4 plus 0 is here. L4 plus 4 is here. L4 plus 8 plus 12, 16, 20, 24. Okay, so 24 down is the label LC5. And so we go to LC5. And we see that at address LC5, it is a string. So it is returning this memory address right here. And so it is going to put string right here. So it loads into register 0 that string. And then it calls put string, and it prints the string to the screen. And then it moves R3 into R0 and basically quits it quits at that point. So your goal is somehow, and I'm not going to tell you how, but somehow to find the code that is checking to see if the password is correct and make it accept anything. Okay? So make it so that the user can type in any password and it will accept it. 42 should work, 21 should work, -11 should work. I'm not going to tell you guys what you need to change in your code, but if there's something in there that's seeing if the answer is equal to 42, you should change it so that it always accepts the number. Okay? And so there's 3 of these things that you're going to do. And we're out of time. Locksmith 1 is easy. Hopefully from what was on the screen there, you should have a pretty good idea that there's 2 letters you need to change to win. Locksmith 2 is medium difficulty, and Locksmith 3 is hard difficulty. Okay? So they're all basically the same. Enter a password, you know. And your task is to make it accept any password. Okay. So sudo deploy homework to csci 45 locksmith. Locksmith 2, and Locksmith 3. But yeah, but in all seriousness, reverse engineering is actually a protected activity. It's not always illegal. And you can look at how programs do things to learn how they work. And you can reverse engineer them for compatibility purposes and things like that. So don't pirate software. It's illegal and stuff. I don't know. Unless you pay for it and then they don't give it to you, in which case... 1 and 2 are homework, 3 extra credit? No. No, all 3 of them are homework. So, last year I don't think anybody solved Locksmith 3 though. So, Sony reverse engineered a Sega Genesis when making the PS2, yeah. So, yeah, I don't think anyone last year solved Locksmith 3. Most people were able to do 1 and 2. And so if you're able to do 1 and 2, I don't know how many points you'll get. 1, all of you guys should be able to do in about 10 seconds. 2, medium difficulty, and like I said, 3, it's some high schoolers' Hangman program. And what happens is if you type in the, it's actually kind of funny. If you type in the password wrong, welcome to Hangman, Apple, A, P, no matter what you type in, it's wrong. So if you get the password wrong, it hangmans you no matter what. Right? So passkey is 15. Okay. Apple, A, P. No matter what you do, it hangmans you. Okay. So what you need to do is make it so that the passcode works for Locksmith 3. So it'll tell you the passkey is 29, but right now it doesn't matter what you type in. It hangmans you no matter what. Okay? So for passcode 3, for Locksmith 3, you just need to make the passcode work. Oh, order 66. Perfect. Look at that. So you need to make it so that when you type in 66, or really anything, that you can actually play Hangman properly. You can use anything you like. You can use anything you'd like. There is no C file. That's correct. You have assembly. You are given a disassembled version. You are given a disassembled version of an executable, and it is your task to fix it. Okay. A friend of mine fixed Real Audio Player back in the day. He was annoyed by the fact that if there was a copyrighted stream, you couldn't hit the record button on it, and so he opened it up in assembly, found the place where it's saying, if the stream is copyrighted, disable the recording, and he said, nope. Branch never. And then, whatever the x86 equivalent was, saved it, and then he was able to record any audio stream that he wanted on Real Audio. That was a fun project. I was kind of watching over his shoulder as he did it. Okay. Any questions? That's it for class today, guys. Learned something about 2D arrays, 3D arrays. And yeah, for locksmith, just remove copy protection. That's it. Okay, cool. Thanks, guys. And this will be due in a week. I'll start going through your caching worksheets. Oh, I need to grade. What's his face? SpongeBob. Okay, I'll get that taken care of. All right, I'll see you guys.